So now we're going to look at some practice problems. So here's a reaction, and here's the rate law right here. And they ask, what are the reaction orders in this rate law in part A? Well, NO, the exponent is 2, so NO is second order. H2, the exponent is 1, so it's first order. And the overall rate will be 2 plus 1, so it will be third order overall when we add up the orders. So the correct answer here is B. Part B says, does doubling the concentration of NO have the same effect on the rate as doubling the concentration of H2? No, because these orders are different. So if we double the NO concentration, we would expect the rate to go up by 4 times. Okay, it would do the square of whatever we had done to the NO. If we double the H2, we would expect the rate to only go up twice. The rate would also double. Since it's first order, it would do whatever had happened to the concentration, the rate would do the same. Now here, once we have the rate law, we can find the rate constant using data from the table. And the units of K, the rate constants, will depend on the overall reaction order. The magnitude of K is going to indicate whether a reaction is fast or slow. So large values of K, 10 to the 9th or higher, will be fast. Small values of K, 10 or less, are slow reactions. So in this example, we can use the data and the rate law from experiment 1 to calculate the rate constant. We found that the rate law was rate equals K times NH4 plus times NO2 minus. So if we use experiment number 1, we can plug these values into this and solve for the rate constant. So I can put in here 5.4 times 10 to the minus 7 for the rate. We can put K is what we're looking for. NH4 plus is going to be 0.01 molar. NO2 minus will be 0.2 molar. Okay, so then we can go ahead and solve for K by isolating it. And so we'll divide this side by 0.01 molar and times 0.2 molar. That cancels that out, but we got to do the same thing on the other side. Okay, so then when we take a look here, after solving for this, after doing our math here, K equals 0.00027 over molarities times seconds. So there's our rate constant. Once we have the rate constant, now we can actually find the rate with different concentrations. So again, here we'll start off with the rate law. Okay, and we will put in the rate constant from before, which was 0.00027 over molarity times seconds. We'll put in these values for our concentrations. 0.100 molar times 0.100 molar, and solve for the rate. So when we plug that into our calculator, we get 2.7 times 10 to the minus 6th molarity per second. Our next practice exercise, you can do that, and the answers are here if you want to check. Now we're going to find a rate law from data here. So this is in your textbook. This is a sample exercise, and it goes through it in the textbook for you as well. So part A, we want to find the rate law for the reaction. So first we want to find how B changes the rate. I could start with A as well. It's not important which one you start with. And so here A is constant, so I'll look at experiments 1 and 2 to figure out how the rate changes when B changes. So I can see here already that when B changes, it doubles here. Look at what happens to the rate. Nothing. Okay, so nothing happens to the rate. So I can see already that when B, I can say when B doubles, rate does not change. And so B is zero order, right? That's what it means to be zero order. The rate does not change even if you change the concentration of B. I could also show this through math, but I think it's often easier when you see that lack of change, even though one reactant is changing, you can just go right to the zero order for B. For finding how A changes the rate, we need to find a place where B is changing, where B is constant and A is changing. So that would be experiments 1 and 3. So here we can do A for 3 over A for 1, okay? And that's related to the rate of 3 over the rate of 1. So let's see how these are related, and I can put a little variable here for the order. And so if I put in the rate of 3, 16.0 times 10 to the minus 5th molarity per second, I put that over the rate of 1, that's 4.0 times 10 to the minus 5th molarity per second. And I put in what the concentration of A is in 3, that's 0.2 to the x over 0.1 to the x. I can divide these out. That's equal to 4, and this is equal to 2 to the x. So here we can see that x has to equal 2 in order for this to be true. So A is second order. Okay, so A is second order. And right here, we can now write the rate law. So the rate is going to be equal to K times A squared. And B is not there because it is zero order. Anything to the 0th power is 1, so it won't appear. Okay, so then in part B, let me move this down here. So part B, I'll do that down here. They would like the rate constant. So again, I can solve for my rate constant by using experiment number 1's data. So using experiment 1, I can put in the rate equals K times A squared. So I can put in 4 times 0 times 10 to the minus 5th molarity per second equals my K times my concentration of A squared. And that would be molarity, right there, 0.1 molar squared. And so I can solve for K, And when I solve for K, I get 4.0 times 10 to the minus 3, 1 over molarity seconds. Okay, and then for part C, they're asking for the rate of reaction when A equals this and B equals that. We can plug into the rate law again. We now have K, so I can use my K from part B, 4.0 times 10 to the minus 3 over molarity times seconds times my 0.050 molar squared, and I get 1.0 times 10 to the minus 5th molarity per second. Okay, so that's my my rate when given these conditions. Here's a next question. So in class, I asked people to work out these two problems. So at this point, you should take a moment and do practice exercise 14.6 and try practice question 1, which goes on to the next slide. And so take a look at these, and I'm going to pause the video here and take a minute to complete these. I gave people about 20 minutes to complete these two problems. And so I'll show you the solution in a moment. Okay, so again, for part A, to determine the rate law, we need to figure out how each of these reactants changes the initial rate. So in part A, first I will find where NO is not changing as constant and H2 changes. So first I'll find how H2 affects the rate. And I don't need to do H2 first, right? I could pick the other one. So I'm going to use experiment 1 and 2. So I'll use experiment 1 and 2 and take a look here. I can see that this is going up 2 times, and this is also going up 2 times. But if I can't see that, I'm going to use my math. I'll take my rate of 2 over the rate of 1, and that will equal my H2 concentration to the x power, my second one, over my H2 concentration for first. And I can plug these numbers in. So I would have 2.46 times 10 to the minus 3 molarity per second over 1.23 times 10 to the minus 3 molarity per second equals my H2 concentration from experiment 2 to the x power over my concentration from part 1, from experiment 1 to the x power. And so I can see here that this is equal to 2, and this is equal to 2 to the x. So x equals 1. Okay, so the H2 is first order. Now we got to figure out how the NO affects rate. So to look at this, I'm going to find 2 where H2 is constant. That would be experiment 1 and 3, and NO is doubling there. So I can use experiment 1 and 3. So let me take my rate of 3 over my rate of 1, and that will be my NO from experiment 3 to the y power, and NO from experiment 1 to the y power. I'm going to plug in my values here, 4.92 times 10 to the minus 3 molarity per second over 1.23 times 10 to the minus 3 molarity per second. that equals my NO, my 0.2 molar to the Y over my 0.1 molar to the Y. And I can see here that this is equal to 4 when I divide that out. And this is 2 to the Y. So Y has to equal 2. So based on these orders now, I can write my rate law. My rate law is going to be rate equals K times my H2 to the first power, and then my NO to the second power. So there's my rate law for part A. For part B, again, calculate the rate constant. We're going to plug in using experiment 1 to plug in to this. Okay, so if we take a look here, we can put in for the rate 1.23 times 10 to the minus 3 molarity per second equals K times my value of H2 for experiment 1 is 0.1 molar. And then my N2 for experiment 1 is also 0.1 molar, but that's squared. And so when I solve for that, I will end up with K equals 1.21 over molarity squared times seconds. All right, so that's my rate constant in B. And then plugging in for my rate in part C, I can put in my rate constant, 1.2, no times, molarity squared per second times my 0.50. Oh, sorry, we got to put in my hydrogen first, times my 0.50 molar squared. And then solving for that, we get 0. Sorry, we should work this out, times 0.15 times 0.05 squared equals 0.00045. And the units are going to be molarity per second. Okay, so that is that problem. And then the practice question here, when you do it out, you can take a look at the annotated notes, but you will end up with this first question. This will be first order. And then part 2, since the rate doubles, you should get for the OH minus, get 0.0200 molar. And then using particle level reasoning, you could give 2 explanations. The 2 explanations are fewer collisions, due to lower velocity of molecules. Okay, and the second reason is that the collisions will have less force due to lower kinetic energy. Okay, so less molecules will overcome the activation barrier. Okay, so they will collide with less force, and so less of them will have enough kinetic energy to to break apart those bonds and turn into the products. Okay, so if you have any questions, please let me know. And that's the end of part two's class video.